after being rubbed appear to attract other bodies was known to the ancients. In modern times, a great variety of other phenomena have been observed and have been found to be related to these phenomena of attraction. They have been classed under the name of electric phenomena, amber, electron, having been the substance in which they were first described. Other bodies, particularly the lodestone and pieces of iron and steel which have been subjected to certain processes, have also been long known to exhibit phenomena of action at a distance. These phenomena, with others related to them, were found to differ from the electric phenomena and have been classed under the name of magnetic phenomena, the lodestone, magnes, being found in the Thessalian Magnesia. These two classes of phenomena have since been found to be related to each other, and the relations between the various phenomena of both classes, so far as they are known, constitute the science of electromagnetism. In the following treatise, I propose to describe the most important of these phenomena, to show how they may be subjected to measurement, and to trace the mathematical connections of the quantities measured. Having thus obtained the data for a mathematical theory of electromagnetism, and having shown how this theory may be applied to the calculation of phenomena, I shall endeavor to place in as clear a light as I can the relations between the mathematical form of this theory and that of the fundamental science of dynamics, in order that we may be in some degree prepared to determine the kind of dynamical phenomena among which we are to look for illustrations or explanations of the electromagnetic phenomena. In describing the phenomena, I shall select those which most clearly illustrate the fundamental ideas of the theory, omitting others, or reserving them till the reader is more advanced. The most important aspect of any phenomenon from a mathematical point of view is that of a measurable quantity. I shall therefore consider electrical phenomena chiefly with a view to their measurement, describing the methods of measurement and defining the standards on which they depend. In the application of mathematics to the calculation of electrical quantities, I shall endeavor in the first place to deduce the most general conclusions from the data at our disposal, and in the next place to apply the results to the simplest cases that can be chosen. I shall avoid as much as I can those questions which, though they have elicited the skill of mathematicians, have not enlarged our knowledge of science. The internal relations of the different branches of the science which we have to study are more numerous and complex than those of any other science hitherto developed. Its external relations on the one hand to dynamics and on the other to heat, light, chemical action, and the constitution of bodies seem to indicate the special importance of electrical science as an aid to the interpretation of nature. It appears to me, therefore, that the study of electromagnetism in all its extent has now become of the first importance as a means of promoting the progress of science. The mathematical laws of the different classes of phenomena have been to a great extent satisfactorily made out. The connections between the different classes of phenomena have also been investigated, and the probability of the rigorous exactness of the experimental laws has been greatly strengthened by a more extended knowledge of their relations to each other. Finally, some progress has been made in the reduction of electromagnetism to a dynamical science by showing that no electromagnetic phenomenon is contradictory to the supposition that it depends on purely dynamical action. What has been hitherto done, however, has by no means exhausted the field of electrical research. It has rather opened up that field by pointing out subjects of inquiry and furnishing us with means of investigation. It is hardly necessary to enlarge upon the beneficial results of magnetic research on navigation, and the importance of a knowledge of the true direction of the compass and of the effect of the iron in a ship. But the labors of those who have endeavored to render navigation more secure by means of magnetic observations have at the same time greatly advanced the progress of pure science. Gauss, as a member of the German Magnetic Union, brought his powerful intellect to bear on the theory of magnetism and on the methods of observing it, and he not only added greatly to our knowledge of the theory of attractions, but reconstructed the whole of magnetic science as regards the instruments used, the methods of observation, and the calculation of the results, so that his memoirs on terrestrial magnetism may be taken as models of physical research by all those who are engaged in the measurement of any of the forces in nature. The important applications of electromagnetism to telegraphy have also reacted on pure science by giving a commercial value to accurate electrical measurements, and by affording to electricians the use of apparatus on a scale which greatly transcends that of any ordinary laboratory. The consequences of this demand for electrical knowledge and of these experimental opportunities for acquiring it have been already very great, both in stimulating the energies of advanced electricians and in diffusing among practical men a degree of accurate knowledge which is likely to conduce to the general scientific progress of the whole engineering profession. There are several treatises in which electrical and magnetic phenomena are described in a popular way. These, however, are not what is wanted by those who have been brought face to face with quantities to be measured, and whose minds do not rest satisfied with lecture room experiments. There is also a considerable mass of mathematical memoirs, which are of great importance in electrical science, but they lie concealed in the bulky transactions of learned societies. They do not form a connected system. They are of very unequal merit, and they are for the most part beyond the comprehension of any but professed mathematicians. I have therefore thought that a treatise would be useful, which should have for its principal object to take up the whole subject in a methodical manner, and which should also indicate how each part of the subject is brought within the reach of methods of verification by actual measurement. The general complexion of the treatise differs considerably from that of several excellent electrical works, published, most of them, in Germany, and it may appear that scant justice is done to the speculations of several eminent electricians and mathematicians. One reason of this is that before I began the study of electricity, I resolved to read no mathematics on the subject, till I had first read through Faraday's experimental researches on electricity. I was aware that there was supposed to be a difference between Faraday's way of conceiving phenomena and that of the mathematicians, so that neither he nor they were satisfied with each other's language. I had also the conviction that this discrepancy did not arise from either party being wrong. I was first convinced of this by Sir William Thomson, to whose advice and assistance, as well as to his published papers, I owe most of what I have learned on the subject. As I proceeded with the study of Faraday, I perceived that his method of conceiving the phenomena was also a mathematical one, though not exhibited in the conventional form of mathematical symbols. I also found that these methods were capable of being expressed in the ordinary mathematical forms, and thus compared with those of the professed mathematicians. For instance, Faraday, in his mind's eye, saw lines of force traversing all space where the mathematicians saw centers of force attracting at a distance. Faraday saw a medium where they saw nothing but distance. Faraday sought the seat of the phenomena in real actions going on in the medium. They were satisfied that they had found it in a power of action at a distance impressed on the electric fluids. When I had translated what I considered to be Faraday's ideas into a mathematical form, I found that in general, the results of the two methods coincided, so that the same phenomena were accounted for, and the same laws of action deduced, whether we adopted Faraday's method of lines of force or the ordinary mathematical method. I also found that several of the most fertile methods of research discovered by the mathematicians could be expressed much better in terms of ideas derived from Faraday than in their original form. The whole theory, for instance, of the potential considered as a quantity which satisfies a certain partial differential equation belongs essentially to the method which I have called that of Faraday. According to the other method, the potential, if it is to be considered at all, must be regarded as the result of a summation of the electrified particles divided each by its distance from a given point. Hence, many of the mathematical discoveries of Laplace, Poisson, Green, and Gauss find their proper place in this treatise, and their appropriate expression in terms of conceptions mainly derived from Faraday. Great progress has been made in electrical science, chiefly in Germany, by cultivators of the theory of action at a distance. The valuable electrical measurements of W. Weber are interpreted by him according to this theory, and the electromagnetic speculation, which was originated by Gauss and carried on by Weber, Riemann, J. and C. Neumann, Lorentz, and others, is founded on the theory of action at a distance, but depending either directly on the relative velocity of the particles or on the gradual propagation of something, whether potential or force, from the one particle to the other. The great success which these eminent men have attained in the application of mathematics to electrical phenomena gives, as is natural, additional weight to their theoretical speculations, so that those who, as students of electricity, turn to them as the greatest authorities in mathematical electricity, would probably imbibe, along with their mathematical methods, their physical hypotheses. These physical hypotheses, however, are entirely alien from the way of looking at things which I adopt. And one object which I have in view is that some of those who wish to study electricity may, by reading this treatise, come to see that there is another way of treating the subject, which is no less fitted to explain the phenomena, and which, though in some parts it may appear less definite, corresponds, as I think, more faithfully with our actual knowledge, both in what it affirms and in what it leaves undecided. In a philosophical point of view, moreover, it is exceedingly important that two methods should be compared, both of which have succeeded in explaining the principal electromagnetic phenomena, and both of which have attempted to explain the propagation of light as an electromagnetic phenomenon, and have actually calculated its velocity, while at the same time the fundamental conceptions of what actually takes place, as well as most of the secondary conceptions of the quantities concerned, are radically different. I have therefore taken the part of an advocate rather than that of a judge, and have rather exemplified one and attempted to give an impartial description of both. I have no doubt that the method which I have called the German one will also find its supporters, and will be expounded with a skill worthy of its ingenuity. I have not attempted an exhaustive account of electrical phenomena, experiments, and apparatus. The student who desires to read all that is known on these subjects will find great assistance from the Traité d'électricité of Professor A. de la Rive, and from several German treatises, such as Wiedemann's Galvanismus, Riess' Reibungselektrizität, Beer's Einleitung in die Elektrostatik, and others. I have confined myself almost entirely to the mathematical treatment of the subject, but I would recommend the student, after he has learned, experimentally if possible, what are the phenomena to be observed, to read carefully Faraday's experimental researches in electricity. He will there find a strictly contemporary historical account of some of the greatest electrical discoveries and investigations that carried on in an order and succession which could hardly have been improved if the results had been known from the first, and expressed in the language of a man who devoted much of his attention to the methods of accurately describing scientific operations and their results. It is of great advantage to the student of any subject to read the original memoirs on that subject, for science is always most completely assimilated when it is in the nascent state, and in the case of Faraday's researches, this is comparatively easy, as they are published in a separate form, and may be read consecutively. If by anything I have here written I may assist any student in understanding Faraday's modes of thought and expression, I shall regard it as the accomplishment of one of my principal aims, to communicate to others the same delight which I have found myself in reading Faraday's researches. The description of the phenomena and the elementary parts of the theory of each subject will be found in the earlier chapters of each of the 4 parts into which this treatise is divided. The student will find in these chapters enough to give him an elementary acquaintance with the whole science. The remaining chapters of each part are occupied with the higher parts of the theory, the processes of numerical calculation, and the instruments and methods of experimental research. The relations between electromagnetic phenomena and those of radiation, the theory of molecular electric currents, and the results of speculation on the nature of action at a distance are treated of in the last 4 chapters of the 2nd volume. February 1st, 1873. Electricity and Magnetism. Preliminary. On the measurement of quantities. 1. Every expression of a quantity consists of 2 factors or components. One of these is the name of a certain known quantity of the same kind as the quantity to be expressed, which is taken as a standard of reference. The other component is the number of times the standard is to be taken in order to make up the required quantity. The standard quantity is technically called the unit, and the number is called the numerical value of the quantity. There must be as many different units as there are different kinds of quantities to be measured. But in all dynamical sciences, it is possible to define these units in terms of the three fundamental units of length, time, and mass. Thus, the units of area and of volume are defined respectively as the square and the cube, whose sides are the unit of length. Sometimes, however, we find several units of the same kind founded on independent considerations. Thus, the gallon, or the volume of 10 pounds of water, is used as a unit of capacity as well as the cubic foot. The gallon may be a convenient measure in some cases, but it is not a systematic one, since its numerical relation to the cubic foot is not a round integral number. 2. In framing a mathematical system, we suppose the fundamental units of length, time, and mass to be given, and deduce all the derivative units from these by the simplest attainable definitions. The ultimate ratio at which we arrive must be such that a person of any nation, by substituting for the different symbols the numerical value of the quantities as measured by his own national units, would arrive at a true result. Hence, in all scientific studies, it is of the greatest importance to employ units belonging to a properly defined system, and to know the relations of those units to the fundamental units, so that we may be able at once to transform our results from one system to another. This is most conveniently done by ascertaining the dimensions of every unit in terms of the three fundamental units. When a given unit varies as the nth power of one of these units, it is said to be of n dimensions as regards that unit. For instance, the scientific unit of volume is always the cube whose side is the unit of length. If the unit of length varies, the unit of volume will vary as its third power, and the unit of volume is said to be of 3 dimensions with respect to the unit of length. A knowledge of the dimensions of units furnishes a test which ought to be applied to the equations resulting from any lengthened investigation. The dimensions of every term of such an equation with respect to each of the 3 fundamental units must be the same. If not, the equation is absurd and contains some error, as its interpretation would be different according to the arbitrary system of units which we adopt. The 3 fundamental units. 3. Length. The standard of length for scientific purposes in this country is 1 foot, which is the third part of the standard yard preserved in the Exchequer chambers. In France, and in other countries which have adopted the metric system, it is the meter. The meter is theoretically the 10 millionth part of the length of a meridian of the Earth measured from the pole to the equator. But practically, it is the length of a standard preserved in Paris, which was constructed by Borda to correspond when at the temperature of melting ice with the value of the preceding length as measured by Delambre. The meter has not been altered to correspond with new and more accurate measurements of the Earth, but the error of the meridian is estimated in terms of the original meter. In astronomy, the mean distance of the Earth from the Sun is sometimes taken as a unit of length. In the present state of science, the most universal standard of length, which we could assume would be the wavelength in vacuum of a particular kind of light, emitted by some widely diffused substance, such as sodium, which has well-defined lines in its spectrum. Such a standard would be independent of any changes in the dimensions of the Earth, and should be adopted by those who expect their writings to be more permanent than that body. In treating of the dimensions of units, we shall call the unit of length L. If L is the numerical value of a length, it is understood to be expressed in terms of the concrete unit L, so that the actual length would be fully expressed by L times L. 4. Time. The standard unit of time in all civilized countries is deduced from the time of rotation of the Earth about its axis. The sidereal day, or the true period of rotation of the Earth, can be ascertained with great exactness by the ordinary observations of astronomers, and the mean solar day can be deduced from this by our knowledge of the length of the year. The unit of time adopted in all physical researches is 1 second of mean solar time. In astronomy, a year is sometimes used as a unit of time. A more universal unit of time might be found by taking the periodic time of vibration of the particular kind of light whose wavelength is the unit of length. We shall call the concrete unit of time t and the numerical measure of time t. 5. Mass. The standard unit of mass is in this country the avoirdupois pound, preserved in the exchequer chambers. The grain, which is often used as a unit, is defined to be the thousandth part of this pound. In the metrical system, it is the gram, which is theoretically the mass of a cubic centimeter of distilled water at standard temperature and pressure, but practically it is the thousandth part of a standard kilogram preserved in Paris. The inconvenience arising when the masses of bodies can be compared only by their weights is far greater than that hitherto attending the measurement of lengths, so that all masses ought, if possible, to be represented directly. In astronomy and in many of the most important sciences, the unit of mass of the Earth is sometimes taken as a unit, but in universal dynamical theory of astronomy, the unit of mass is deduced from the units of time and length, combined with the fact of universal gravitation. The astronomical unit of mass is that mass which attracts another body placed at the unit of distance so as to produce in that body the unit of acceleration. In framing a universal system of units, we may either deduce the unit of mass in this way from those of length and time already defined, and this we can do to a rough approximation in the present state of science, or if we expect soon to be able to determine the mass of a single molecule of a standard substance, we may wait for this determination before fixing a universal standard of mass. We shall denote the concrete unit of mass by m in treating of the dimensions of other units. The unit of mass will be taken as one of the three fundamental units. When, as in the French system, a particular substance, water, is taken as a standard of density, then the unit of mass is no longer independent, but varies as the unit of volume, or as L cubed. If, as in the astronomical system, the unit of mass is defined with respect to its attractive power, the dimensions of m are L cubed t to the power -2. For the acceleration due to the attraction of a mass m at a distance r is by the Newtonian law m/r². Suppose this attraction to act for a very small time t on a body originally at rest, and to cause it to describe a space s, then by the formula of Galileo, s equals 1/2 ft squared and f equals m/r². Since r and s are both lengths and t is a time, this equation cannot be true unless the dimensions of m are L cubed t to the power -2. The same can be shown from any astronomical equation in which the mass of a body appears in some, but not in all terms of the equation. The unit of velocity is that velocity in which unit of length is described in unit of time. Its dimensions are Lt to the power -1. If we adopt the units of length and time derived from the vibrations of light, then the unit of velocity is the velocity of light. The unit of acceleration is that acceleration in which the velocity increases by unity in unit of time. Its dimensions are Lt to the power -2. The unit of density is the density of a substance which contains unit of mass in unit of volume. Its dimensions are ml to the power -3. The unit of momentum is the momentum of unit of mass moving with unit of velocity. Its dimensions are mlt to the power -1. The unit of force is the force which produces unit of momentum in unit of time. Its dimensions are mlt to the power -2. This is the absolute unit of force, and this definition of it is implied in every equation in dynamics. Nevertheless, in many textbooks in which these equations are given, a different unit of force is adopted, namely the weight of the national unit of mass, and then, in order to satisfy the equations, the national unit of mass is itself abandoned, and an artificial unit is adopted as the dynamical unit, equal to the national unit divided by the numerical value of the force of gravity at the place. In this way, both the unit of force and the unit of mass are made to depend on the value of the force of gravity, which varies from place to place, so that statements involving these quantities are not complete without a knowledge of the force of gravity in the places where these statements were found to be true. The abolition, for all scientific purposes, of this method of measuring forces is mainly due to the introduction of a general system of making observations of magnetic force in countries in which the force of gravity is different. All such forces are now measured according to the strictly dynamical method deduced from our definitions, and the numerical results are the same in whatever country the experiments are made. The unit of work is the work done by the unit of force acting through the unit of length measured in its own direction. Its dimensions are ml squared t to the power -2. The energy of a system, being its capacity of performing work, is measured by the same unit as work. The definitions of other quantities and of the units to which they are referred will be given when we require them. In transforming the values of physical quantities determined in terms of one unit so as to express them in terms of any other unit of the same kind, we have only to remember that every expression for the quantity consists of two factors, the unit and the numerical part, which expresses how often the unit is to be taken. Hence, the numerical part of the expression varies inversely as the magnitude of the unit, that is, inversely as the various powers of the fundamental units which are indicated by the dimensions of the derived unit. On physical continuity and discontinuity. 7. A quantity is said to vary continuously when, if it passes from one value to another, it assumes all the intermediate values. We may obtain the conception of continuity from a consideration of the continuous existence of a particle of matter in time and space. Such a particle cannot pass from one position to another without describing a continuous line in space, and the coordinates of its position must be continuous functions of the time. In the so-called equation of continuity, as given in treatises on hydrodynamics, the fact expressed is that matter cannot appear in or disappear from an element of volume without passing in or out through the sides of that element. A quantity is said to be a continuous function of its variables when, if the variables alter continuously, the quantity itself alters continuously. Thus, if w is a function of x, and if while x passes continuously from x0 to x1, w passes continuously from w0 to w1. But when x passes from x1 to x2, w passes from w1 to w2, w1 being different from w2, then w is said to have a discontinuity in its variation with respect to x, for the value x equals x1, because it passes abruptly from w1 to w2, while x passes continuously through x1. If we consider the differential coefficient of w with respect to x for the value x equals x1 as the limit of the fraction w2 minus w0 over x2 minus x0, when x0 and x2 are both made to approach x1 without limit, then if x0 and x2 are always on opposite sides of x1, the ultimate value of the numerator will be w1 minus w0 and w2 minus w1, and that of the denominator will be 0, so that the differential coefficient will be infinite. Hence, a function of x which has a real discontinuity in its value can exist only with respect to the particular variable x. We must in this case admit that it has an infinite differential coefficient when x equals x1. If it is not physically continuous, it cannot be differentiated at all. It is possible in physical questions to get rid of the idea of discontinuity without sensibly altering the conditions of the case. If x0 is a very little less than x1 and x2 a very little greater than x1, then w0 will be very nearly equal to w1 and w2 to w1. We may now suppose w to vary in any arbitrary but continuous manner from w0 to w2 between the limits x0 and x2. In many physical questions, we may begin with a hypothesis of this kind, and then investigate the result when the values of x0 and x2 are made to approach that of x1 and ultimately to reach it. The result will, in most cases, be independent of the arbitrary manner in which we have supposed w to vary between the limits. Discontinuity of a function of more than one variable. 8. If we suppose the values of all the variables except x to be constant, the discontinuity of the function will occur for particular values of x, and these will be connected with the values of the other variables by an equation which we may write phi equals phi of x, y, z, and so on equals 0. The discontinuity will occur when phi equals 0. When phi is positive, the function will have the form f2 of x, y, z, and so on. When phi is negative, it will have the form f1 of x, y, z, and so on. There need be no necessary relation between the forms f1 and f2. To express this discontinuity in a mathematical form, let one of the variables, say x, be expressed as a function of phi and the other variables, and let f1 and f2 be expressed as functions of phi, y, z, and so on. We may now express the general form of the function by any formula which is sensibly equal to f2 when phi is positive and to f1 when phi is negative. Such a formula is the following: f equals f1 plus n phi over 1 plus e to the n phi times f2 minus f1. As long as n is a finite quantity, however great, f will be a continuous function, but if we make n infinite, f will be equal to f2 when phi is positive and equal to f1 when phi is negative. Discontinuity of the derivatives of a continuous function. Let the values of the variables for which the discontinuity of the derivatives occurs be connected by the equation phi equals phi of x, y, z, and so on equals 0, and let f1 and f2 be expressed in terms of phi and n minus one other variables, say y, z, and so on. Then, when phi is negative, f1 is to be taken, and when phi is positive, f2 is to be taken. And since f is itself continuous, when phi is 0, f1 equals f2. Hence, when phi is 0, the derivatives df1 over d phi and df2 over d phi may be different, but the derivatives with respect to any of the other variables, such as df1 over dy and df2 over dy, must be the same. The discontinuity is therefore confined to the derivative with respect to phi, all the other derivatives being continuous. Functions. 9. If u is a function of x such that its value is the same for x, x plus na, and all values of x differing by a, u is called a periodic function of x, and a is called its period. If x is considered as a function of u, then for a given value of u, there must be an infinite series of values of x differing by multiples of a. In this case, x is called a multiple function of u, and a is called its cyclic constant. The differential coefficient dx over du has only a finite number of values corresponding to a given value of u. On the relation of physical quantities to directions in space. 10. In distinguishing the kinds of physical quantities, it is of great importance to know how they are related to the directions of those coordinate axes, which we usually employ in defining the positions of things. The introduction of coordinate axes into geometry by Descartes was one of the greatest steps in mathematical progress, for it reduced the methods of geometry to calculations performed on numerical quantities. The position of a point is made to depend on the length of three lines, which are always drawn in determinate directions, and the line joining two points is in like manner considered as the resultant of three lines. But for many purposes in physical reasoning, as distinguished from calculation, it is desirable to avoid explicitly introducing the Cartesian coordinates, and to fix the mind at once on a point of space instead of its three coordinates, and on the magnitude and direction of a force instead of its three components. This mode of contemplating geometrical and physical quantities is more primitive and more natural than the other, although the ideas connected with it did not receive their full development till Hamilton made the next great step in dealing with space, by the invention of his calculus of quaternions. As the methods of Descartes are still the most familiar to students of science, and as they are really the most useful for purposes of calculation, we shall express all our results in the Cartesian form. I am convinced, however, that the introduction of the ideas, as distinguished from the operations and methods of quaternions, will be of great use to us in the study of all parts of our subject, and especially in electrodynamics, where we have to deal with a number of physical quantities, the relations of which to each other can be expressed far more simply by a few words of Hamilton's than by the ordinary equations. 11. One of the most important features of Hamilton's method is the division of quantities into scalars and vectors. A scalar quantity is capable of being completely defined by a single numerical specification. Its numerical value does not in any way depend on the directions we assume for the coordinate axes. A vector, or directed quantity, requires for its definition three numerical specifications, and these may most simply be understood as having reference to the directions of the coordinate axes. Scalar quantities do not involve direction. The volume of a geometrical figure, the mass and the energy of a material body, the hydrostatical pressure at a point in a fluid, and the potential at a point in space are examples of scalar quantities. A vector quantity has direction as well as magnitude, and is such that a reversal of its direction reverses its sign. The displacement of a point, represented by a straight line drawn from its original to its final position, may be taken as the typical vector quantity, from which indeed the name of vector is derived. The velocity of a body, its momentum, the force acting on it, an electric current, The magnetization of a particle of iron are instances of vector quantities. There are physical quantities of another kind which are related to directions in space, but which are not vectors. Stresses and strains in solid bodies are examples of these, and the properties of bodies considered in the theory of elasticity and in the theory of double refraction. Quantities of this class require for their definition 9 numerical specifications. They are expressed in the language of quaternions by linear and vector functions of a vector. The addition of one vector quantity to another of the same kind is performed according to the rule given in statics for the composition of forces. In fact, the proof which Poisson gives of the parallelogram of forces is applicable to the composition of any quantities, such that a reversal of their sign is equivalent to turning them end for end. When we wish to denote a vector quantity by a single symbol and to call attention to the fact that it is a vector, so that we must consider its direction as well as its magnitude, we shall denote it by a German capital letter as V, S, and so on. In the calculus of quaternions, the position of a point in space is defined by the vector drawn from a fixed point, called the origin, to that point. If at that point of space we have to consider any physical quantity whose value depends on the position of the point, that quantity is treated as a function of the vector drawn from the origin. The function may be itself either scalar or vector. The density of a body, its temperature, its hydrostatic pressure, the potential at a point are examples of scalar functions. The resultant force at the point, the velocity of a fluid at that point, the velocity of rotation of an element of the fluid, and the couple producing rotation are examples of vector functions. 12. Physical vector quantities may be divided into two classes, in one of which the quantity is defined with reference to a line, while in the other the quantity is defined with reference to an area. For instance, the resultant of an attractive force in any direction may be measured by finding the work which it would do on a body if the body were moved a short distance in that direction, and dividing it by that short distance. Here, the attractive force is defined with reference to a line. On the other hand, the flux of heat in any direction at any point of a solid body may be defined as the quantity of heat which crosses a small area drawn perpendicular to that direction, divided by that area and by the time. Here the flux is defined with reference to an area. There are certain cases in which a quantity may be measured with reference to a line as well as with reference to an area. Thus, in treating of the displacements of elastic solids, we may direct our attention either to the original and the actual position of a particle, in which case the displacement of the particle is measured by the line drawn from the first position to the second, or we may consider a small area fixed in space and determine what quantity of the solid passes across that area during the displacement. In the same way, the velocity of a fluid may be investigated either with respect to the actual velocity of the individual particles or with respect to the quantity of the fluid which flows through any fixed area. But in these cases, we require to know separately the density of the body as well as the displacement or velocity in order to apply the first method, and whenever we attempt to form a molecular theory, we have to use the second method. In the case of the flow of electricity, we do not know anything of its density or its velocity in the conductor. We only know the value of what, on the fluid theory, would correspond to the product of the density and the velocity. Hence, in all such cases, we must apply the more general method of measurement of the flux across an area. In electrical science, electromotive force and magnetic force belong to the first class, being defined with reference to lines. When we wish to indicate this fact, we may refer to them as forces. On the other hand, electric and magnetic induction and electric currents belong to the second class, being defined with reference to areas. When we wish to indicate this fact, we shall refer to them as fluxes. Each of these forces may be considered as producing or tending to produce its corresponding flux. Thus, electromotive force produces dielectric currents in conductors and tends to produce them in dielectrics. It produces electric induction in dielectrics and probably in conductors also. In the same sense, magnetic force produces magnetic induction. 13. In some cases, the flux is simply proportional to the force and in the same direction, But in other cases, we can only affirm that the direction and magnitude of the flux are functions of the direction and magnitude of the force. The case in which the components of the flux are linear functions of those of the force is discussed in the chapter on the equations of conduction, Article 296. There are in general some coefficients which determine the relation between the force and the flux. In certain cases, we have reason to believe that 6 of these coefficients form 3 pairs of equal quantities. In such cases, the relation between the line of direction of the force and the normal plane of the flux is of the same kind as that between a diameter of an ellipsoid and its conjugate diametral plane. In quaternion language, the one vector is said to be a linear and vector function of the other. And when there are 3 pairs of equal coefficients, the function is said to be self-conjugate. In the case of magnetic induction in iron, the flux, the magnetization of the iron, is not a linear function of the magnetizing force. In all cases, however, the product of the force and the flux resolved in its direction gives a result of scientific importance, and this is always a scalar quantity. 14. There are 2 mathematical operations of frequent occurrence which are appropriate to these 2 classes of vectors or directed quantities. In the case of forces, we have to take the integral along a line of the product of an element of the line and the resolved part of the force along that element. The result of this operation is called the line integral of the force. It represents the work done on a body carried along the line. In certain cases in which the line integral does not depend on the form of the line, but only on the position of its extremities, the line integral is called the potential. In the case of fluxes, we have to take the integral over a surface of the flux through every element of the surface. The result of this operation is called the surface integral of the flux. It represents the quantity which passes through the surface. There are certain surfaces across which there is no flux. If 2 of these surfaces intersect, their line of intersection is a line of flux. In those cases in which the flux is in the same direction as the force, lines of this kind are often called lines of force. It would be more correct, however, to speak of them in electrostatics and magnetics as lines of induction, and in electromagnetics as lines of flow. From the physical point of view, it is not so necessary to be observed for the sake of the mathematical methods. This is the distinction between longitudinal and rotational properties. The direction and magnitude of a quantity may depend upon some action or effect which takes place entirely along a certain line, or it may depend upon something of the nature of rotation about that line as an axis. The laws of combination of directed quantities are the same whether they are longitudinal or rotational, so that there is no difference in the mathematical treatment of the 2 classes, but there may be physical circumstances which indicate to which class we must refer a particular phenomenon. Thus, electrolysis consists of the transfer of certain substances along a line in one direction and of certain other substances in the opposite direction, which is evidently a longitudinal phenomenon, and there is no evidence of any rotational effect about the direction of the force. Hence we infer that the electric current which causes or accompanies electrolysis is a longitudinal and not a rotational phenomenon. On the other hand, the north and south poles of a magnet do not differ as oxygen and hydrogen do, which appear at opposite places during electrolysis, so that we have no evidence that magnetism is a longitudinal phenomenon, while the effect of magnetism in rotating the plane of polarized light distinctly shows that magnetism is a rotational phenomenon. 16. The operation of integration of the resolved part of a vector quantity along a line is important in physical science generally and should be clearly understood. Let x, y, z be the coordinates of a point P on a line whose length, measured from a certain point A, is s. These coordinates will be functions of a single variable s. Let r be the value of the vector quantity at P, and let the tangent to the curve at P make with the direction of r the angle epsilon. Then r cosine epsilon is the resolved part of r along the line, and the integral L equals the integral from 0 to s of r cosine epsilon ds is called the line integral of r along the line s. We may write this expression L equals the integral from 0 to s of open parentheses x dx over ds plus y dy over ds plus z dz over ds close parentheses ds, where x, y, z are the components of r parallel to x, y, z, respectively. This quantity is, in general, different for different lines drawn between A and P. When, however, within a certain region, the quantity x dx plus y dy plus z dz equals negative d psi, that is an exact differential within that region, the value of L becomes psi at A minus psi at P, and is the same for any two forms of the path between A and P, provided the one form can be changed into the other by continuous motion without passing out of this region. On potentials. The quantity psi is a scalar function of the position of the point and is therefore independent of the directions of reference. It is called the potential function, and the vector quantity whose components are x, y, z is said to have a potential psi if x equals negative d psi over dx, y equals negative d psi over dy, z equals negative d psi over dz. When a potential function exists, surfaces for which the potential is constant are called equipotential surfaces. The direction of r at any point of such a surface coincides with the normal to the surface, and if n be a normal at the point P, then r equals negative d psi over dn. The method of considering the components of a vector as the first derivatives of a certain function of the coordinates with respect to these coordinates was invented by Laplace in his treatment of the theory of attractions. The name of potential was first given to this function by Green, who made it the basis of his treatment of electricity. Green's essay was neglected by mathematicians till 1846, and before that time, most of its important theorems had been rediscovered by Gauss, Chassel, Sturm, and Thomson. In the theory of gravitation, the potential is taken with the opposite sign to that which is here used, and the resultant force in any direction is then measured by the increase of the potential function in that direction. In electrical and magnetic investigations, the potential is defined so that the resultant force in any direction is measured by the decrease of the potential in that direction. This method of using the expression makes it correspond in sign with potential energy, which always decreases when the bodies are moved in the direction of the forces acting on them. 17. The geometrical nature of the relation between the potential and the vector thus derived from it receives great light from Hamilton's discovery of the form of the operator by which the vector is derived from the potential. The resolved part of the vector in any direction is, as we have seen, the first derivative of the potential with respect to a coordinate drawn in that direction, the sign being reversed. Now, if I, j, k are three unit vectors at right angles to each other, and if x, y, z are the components of the vector f resolved parallel to these vectors, then f equals ix plus jy plus kz. And by what we have said above, if psi is the potential, f equals negative open parentheses I d psi over dx plus j d psi over dy plus k d psi over dz close parenthesis. If we now write del for the operator, del equals id over dx plus jd over dy plus kd over dz, then f equals negative del psi. The symbol of operation del may be interpreted as directing us to measure, in each of three rectangular directions, the rate of increase of psi, and then, considering the quantities thus found as vectors, to compound them into one. This is what we are directed to do by the expression. But we may also consider it as directing us first to find out in what direction psi increases fastest, and then to lay off in that direction a vector representing this rate of increase. M. Lamé, in his Traité de Fonctions Inverses, uses the term differential parameter to express the magnitude of this greatest rate of increase, but neither the term itself nor the mode in which Lamé uses it indicates that the quantity referred to has direction as well as magnitude. On those rare occasions in which I shall have to refer to this relation as a purely geometrical one, I shall call the vector f the slope of the scalar function psi, using the word slope to indicate the direction as well as the magnitude of the most rapid decrease of psi. 18. There are cases, however, in which the conditions dz over dy equals dy over dz, dx over dz equals dz over dx, and dy over dx equals dx over dy, which are those of x dx plus y, dy plus z dz being a complete differential, are fulfilled throughout a certain region of space, and yet the line integral from a to p may be different for two lines, each of which lies wholly within that region. This may be the case if the region is in the form of a ring, and if the two lines from A to P pass through opposite segments of the ring. In this case, the one path cannot be transformed into the other by continuous motion without passing out of the region. We are here led to considerations belonging to the geometry of position, a subject which, though its importance was pointed out by Leibniz and illustrated by Gauss, has been little studied. The most complete treatment of this subject has been given by J.B. Listing. Let there be P points in space, and let L lines of any form be drawn joining these points so that no two lines intersect each other, and no point is left isolated. We shall call a figure composed of lines in this way a diagram. Of these lines, P minus 1 are sufficient to join the P points so as to form a connected system. Every new line completes a loop or closed path, or as we shall call it, a cycle. The number of independent cycles in the diagram is therefore K equals L minus P plus 1. Any closed path drawn along the lines of the diagram is composed of these independent cycles, each being taken any number of times and in either direction. The existence of cycles is called cyclosis, and the number of cycles in a diagram is called its cyclomatic number.